Okay, so may I start?
Yes, you can share your screen.
Okay,
You can
so
start
yeah,
now.
share screen.
So go ahead.
My presentation, share. Let me also do this. Okay, good day everyone. Thank you for joining my presentation. I would like to thank the committee first for their time and for evaluation of my thesis. So as we see, my thesis is entitled Event-Triggered Consensus Frameworks for Multi-Agent Systems. Like in any other presentation, we start with some introduction, then we state the problem of event-triggered consensus, some challenges and contribution of the thesis are listed. Then I selected two proposed implementations for today's presentation. We will have a couple of experimental results, and finally, the future work will conclude the presentation. So, as we know, multi-agent systems is a kind of system that consists of subsystems, also known as agents. They interact with each other to get a cooperative behavior, and the cooperative behavior most of the time is in the form of consensus, formation, containment, leader following, and some other problems. And by agent, we may refer to maybe moving vehicle, sensor node, electric bus, distributed generator. So the definition of agent is totally application specific. In consensus, as we see in the figure, we may have a couple of agents. They start from initial conditions, and then they agree upon a value of interest between themselves. So, for example, consider a sensor network. In the sensor network, we may have some physically distant sensors. They come up with the measurement at the beginning, and then the parameter of interest is to get the average value of all the measurements. Okay. So let's talk about a little bit about formation and containment. So in formation, the agents are desired to finally get a spatial pattern, a predefined pattern, and also in containment, we have some leaders and some followers, and the followers are expected to reach within the convex hull formed by the leaders. So clearly, because we are talking about the cooperative behavior, we need the data transmission scheme because agents need to talk to each other. Generally, we have three different schemes. One of them is the constant time scheme, in which the agents constantly communicate with each other, with the neighbors. So we can understand that this kind of a scheme is a waste of bandwidth and energy resources. A better scheme is sample data, in which we have a clock and the agents are synchronized with the clock. Then there is a sampling period. Then some actions such as measurement and transmission can be conducted based on a periodic manner. So this is definitely better than constant time and results in reduction of communication. Even better nowadays, we have event-triggered schemes in which transmission occurs only after fulfillment of a time-varying condition. So we can see that this is a smarter way, and there is some condition included here. So this scheme, event-triggering scheme, results in a significant reduction compared to those previous ones. And this is the focus of my thesis and my work. Let's see the definition of event-triggered consensus. And by the way, let me call it EDC from now on. So ETC means event-triggered consensus. In event-triggered consensus, we would like to design a distributed control protocol and also a distributed transmission scheme, which transmits only if the proposed event-triggering condition is satisfied, right? So one control protocol and one event-triggering scheme, such that this equation is satisfied, such that this agreement between the states of any two agents in the network approaches zero. So xi is the state value of agent I, and n is the number of agents in the network. There is a special case for this consensus, which is average consensus, in which the states are desired to reach the average value of the initial measurements, the initial states. So in the thesis, I considered both the cases, both the pure consensus, general consensus, and also the special, the average consensus. Okay, so this figure will hopefully let us understand the scheme a little bit better. We have agent here, we have an event detector block, and a controller block also. So we have also a transmitter here and a receiver here, but I didn't include them just for brevity. So the agent comes up with some states, We measure the states. The states are sent to a block called event detector. The event detector also receives the states from the neighbors. Then there is an event triggering condition here. It checks the condition and comes up with two decisions, either 0 or either 1. If the decision is 1, the state is transmitted to neighbors. And also we update our local controller. However, if the decision is 0, we say no event has been detected. And well, the agent continue to keep using the last event, the previous event. So no update is happening if the decision is no. So agents, I already talked about it, is the one that we want to achieve consensus, event detector controller. Yeah, there is one disadvantage with this scheme because there is no sampler here, and we need to consider continuous time measurement and also continuous time checking of the event detection. But if we move on, there is a more practical implementation in which we include a sampler here, and there is also a zero order hold before the agent. So the advantage of this scheme is that the measurement is relaxed to be periodic, and also the receivers can be conducted in a periodic manner. But when we consider the transmission uses both the advantages of sample data and event trigger. So in other words, I can say the transmission happens on a subset of the sampled data. That's why in literature, the researcher calls this sample data event triggered or periodic event triggered. So in the thesis, I also considered both the block diagrams for ETC. Let's briefly go over some design challenges in line with my research and in line with ETC. So first of all, it's consensus guarantee. That is obviously the main objective. We want to get consensus. Otherwise, the problem has not been solved. So with regards to convergence, we may have asymptotic convergence, exponential convergence, or finite time convergence. The control protocol is also something very important, plays a significant role because a poorly designed control protocol, we know that may generate large fluctuating control signals, may lead to, conservative consensus rate, or either very slow or very fast, or in particular in ETC, it may also impact the efficiency of the event triggering scheme. We will comment on that later. Of course, event triggering scheme is very important. We need to come up with not a poorly designed ET scheme because it results in excessive amount of transmission. Well, like in any other control problem, we may have network-induced problems or physical constraints such as communication bandwidth, measurement noise, channel noise, I don't know, packet dropout, communication delay, model uncertainties, and so on. So the more constraints we consider in our problem, the more practical it gets, and of course, the more complicated. So we all know that if we talk about mathematics, we cannot always guarantee some explicit upper bounds or explicit guarantees if we consider so many physical constraints. Distributed design is also a new trend in cooperative behavior. We all know that in the implementation stage, consensus is always distributed. But the new trend is that to consider even distributed in the design stage. So even in the offline stage, design stage, we would like to get rid of the global information, right? The agent model is also playing an important role because the more complex agents results in more complex design. The agent can be a first order agent, a general linear, homogeneous or heterogeneous, a nonlinear agent. So we need to define what type of agent is of interest, when we want to design ATC implementation. Optimality of the design is also important. Because in any other control parameter also, we would like to include a performance index or some kind of optimization. Also recently, the matter of attack, the issue of attack is getting attention in literature and control theory. The attacks are most of the time in types of denial of service, DOS, replay attack, deception attack, or a mixture of them. Directed and undirected communication. Well, ideally, we would like to have a directed implementation, directed scheme, but sometimes mathematics forces us to consider an undirected communication. One matter that is particularly in regards with ETC schemes is the Zeno behavior. Zeno behavior happens when we cannot guarantee a finite number of a finite number of transmissions within a finite time. So very intuitively speaking, the ET scheme, I mean the event triggering scheme, would not be practical because it has to trigger infinite number of events in a finite time, which is not practical. So if we propose an ETC scheme, we should always take care of the Zeno behavior and we should exclude this. Okay, so after talking about some challenges, here are the main contributions of the thesis. Some of the words may not look very familiar, so hopefully after the end of the presentation, they can come back to this and get a better sense of this. But let's briefly go over them. So we proposed a weighted sum optimization approach to improve the efficiency of the event triggering scheme. In one work, we included sample data event triggering for average consensus in the presence of both quantized transmission and also DOS attack. I studied non-fragile controller design for ETC. Also, a co-design optimization is proposed for dynamic event triggering scheme. So we will comment on dynamic event triggering scheme for later, but just for now, consider it as an advanced and very powerful ET scheme. So dynamic event triggering is a kind of ET scheme, but it is very advanced and results in significant reduction of communication. And also in some of the work, we guarantee a more realistic theoretic bound to DOS attacks. Apart from consensus, also I considered sample data dynamic event triggering for stabilization control, which is, well, one of the most important problems in control theory, and also study formation containment control using a dynamic event triggering scheme. So here are the very main contributions of the thesis. This is a table which lists the characteristics of different implementations that we proposed for single order agents. The highlighted items are the advantages of the proposed scheme, and the highlighted in red are the disadvantages. Again, some of them may not look very familiar or doesn't make sense, but the tables are here. We can always come back to this. For single order agents and for presentation, I decided to pick Cs for a study. And also when considering general linear agents, we proposed some implementations. Most of them have already been published in top-tier transactions or top-tier conferences. Again, the green are advantages, the red are disadvantages. And then I chose Rocket, which is our most recent work to be presented here. Okay, let's get started with Cs, framework Cs. Cs stands for Collaborative Event Triggered Average Consensus with Sample Data. It is an implementation for average consensus. It guarantees a predefined exponential rate. It includes a sort of objective function in order to hopefully reduce the number of transmissions and also reduce the steady state error. And the computation complexity of the optimization does not grow with n. So it is irrespective of the network size. The agent dynamics are first order. We denote sampling period as h. The sequence of transmissions or event triggerings are like ni0h, ni1h, all the way to nikh. We define a disagreement vector, which considers the most recent event for agent I and also the most recent event for the neighboring agents. The control protocol is also based on the disagreement vector. And we also consider a K to be designed, a control gain to be designed. A state error is defined also here, which is the difference between the most recent event and the most recent measurement. So considering the measurement error, the disagreement, and a value phi2, the event triggering condition is proposed. So intuitively, it says trigger an event or transmit if the threshold, if the state error exceeds the threshold, and the threshold is a combination of disagreement scaled by a coefficient and another set valued coefficient. But we don't know phi1 and phi2 they are to be designed. So in total, we need to design H, we need to design K, and two event triggering parameters, phi1 and phi2. Let's talk a little bit about some performance observations here. Well, the number of events is reduced if phi1 is increased, if phi2 is increased, and if k is reduced. We can show that. And the steady state error from consensus is reduced if we reduce the value of set value threshold phi2. And consensus convergence rate is also increased if k is large, for larger k. If we consider these items together, we may understand that there are some trade-offs and there may be some conflicting behavior between them. Okay. So before going to the parameter design stage, we should consider some preliminary steps. Let's call them 1, 2, 3, 2, 4. Like in any cooperative behavior, we first come up with the closed loop system, and then we convert the consensus problem into an stability problem in order to get benefit of the Lyapunov stability. So I use the very well-known transformation R, which is the subtraction of the current state vector minus the current average value. So in literature, they show that consensus is guaranteed if and only if R approaches 0. So now the problem of consensus has reduced to a stability problem. So if we get stability conditions for R, then we say average consensus is achieved. We need to use a distributed approach that locally computes the second smallest eigenvalue lambda 2 and the largest eigenvalue of the Laplacian network, Laplacian matrix lambda n. So after this, we use the Lyapunov stability theorem, convex optimization techniques to develop the convex constraints. So let's move on to the next slide. This is theorem 3.1 in Thesis. So it is a kind of optimization problem. It says if the following optimization is feasible, and the optimization has some given variables, a desired convergence rate, sampling period h, and the set value threshold phi2. And then if we solve it, we can compute the control gain and one of the ET conditions, the ET parameters, phi1. And also the following convergence rate is also guaranteed, which is an exponential rate, plus a steady state error. So let's just briefly see what the objective function is really doing here. So we remember that a couple of slides ago, we talked that if we want to reduce the number of events, we should try to enlarge phi1 and try to reduce k. So I figured it as a weighted sum of approach optimization, and I looked at the parameters included to design phi1 and to design k. I said, okay, so if we decrease alpha and if we decrease gamma because they are inversely proportional, so finally phi1 will be increased. And also the same thing, but reversely for k. And also if we look at the steady state error, if we reduce the value of phi2, if we reduce the value of alpha, the steady state error is also reduced. So alpha is also sitting in the objective function. So in the next implementation, which is Rocket, we have a more comprehensive objective function, and I try to comment in more detail on that. So that was the end for C's, but let's just summarize it. It was an implementation for first order agents, and it included an optimization to try to get the optimal value of some of our unknown parameters. But Rocket proposes, considers a more general problem. It considers a consensus for general linear agents. It considers a more complicated event triggering scheme, a DTE scheme, dynamic event triggering scheme, and it also investigates the impact of a class of cyber attacks, which is DOS. So if we look at the important features of Rocket, we say it is powerful. It is powerful in reducing the number of event triggerings because it uses a dynamic event triggering scheme. No steady state error from consensus can be achieved. The consensus can be achieved with no steady state error, and also the DOS will be considered. The contributions of the Rocket, very briefly, again, we use the idea of the co-design optimization to increase the inter-event time, to reduce the number of transmissions. So it results in a structure trade-off between the consensus convergence rate, between the frequency of transmissions, I mean how sparse or how intense the frequencies can be, and the level of resilience to DOS. Also, the designer at the very beginning can have a clear idea how the implementation is going to be resilient to DOS, because it includes an adjustable amount of resilience to DOS. And also, as I said before, the theoretic upper bound for DOS are less conservative, I mean, are more realistic. Let's put it this way. So again, let's have a look at the rocket formulation. As I said, it considers the general linear model for agents. The sequence of event triggerings are shown by TIK. Again, a sort of disagreement vector is used here. It is a kind of the last event, I mean the most recent event plus some exponential term. I can talk about it as an let's say open loop estimation. So it is the difference between the most recent event minus the most recent event from the neighboring nodes. The control protocol is a state feedback. It uses the disagreement vector plus an unknown k. So k is to be designed. The state error is again the difference between the most recent event minus the most recent, I mean the real-time state measurements. So let's have a look at the dynamic event triggering. We can see that the dynamic event triggering is more complicated than before. Again, it looks at the state error, and it says if the state error exceeds the threshold, we can transmit. But the threshold considers another dynamic variable in the form of eta I. So eta I follows the first order differential equation, and then we also consider the impact of eta I accompanied by the disagreement vector. So, but one problem with this scheme, I mean, not problem, but the complication goes up because we need to design K, we need to design phi1 as a matrix, phi2, phi3, phi4, and phi5. So we have more than a couple of unknown parameters to be designed. The first question is how to design all these parameters. Okay. So, here, let's talk about the minimum inter-event time. What is the minimum inter-event time? The minimum inter-event time is the time between two possible consecutive events. So in order to exclude the Zeno behavior, we need to make sure that this lower bound is strictly positive, because if it is strictly positive, then there is no possibility that we trigger infinite number of events. But the MIET, the minimum inter-event time, plays also an important role in sensing how our unknown parameters are impacting the minimum inter-event time, right? So as we see, all of our unknown parameters, phi2, phi1, k, and phi5 are including in the MIET. So one idea to reduce the number of transmissions is to increase the minimum inter-event time. And it makes sense, because if we increase the MIET, so we are seeing a reduction in the number of transmissions. So we say the derivatives of the MIET with respect to some of the parameters, in particular K, phi1, and phi4 are negative. It means that the smaller values for this parameter help in increasing the MIET. Even more precisely, it says that these parameters are inversely proportional to MIET. We do the same thing, the derivatives of MIET with respect to phi2, phi3, and phi5, they are positive. It means that larger of these values help in increasing the MIET. Or even more precisely, these parameters are directly proportional to MIET. So we get these notes, and when we want to propose our objective function, we will get benefit of these observations. Okay, so again, we obtain the closed loop multi-agent systems. Again, use another kind of transformation. In this scheme, we use transformation, which is the eigenvalue decomposition L W J W inverse. This is a kind of transformation they use to convert consensus to stability. So again, like before, we get a system which is a transformed version of 11. However, we know that if R approaches 0, then consensus is guaranteed, and it is a bidirectional condition, if and only if. Again, use a stability theorem and convex optimization to get this. So this is the kind of optimization problem. Again, it is a convex, everything is linear. We have some given variables. desired convergence rate, zeta, some decision variables. We solve this optimization and we can compute reversely these parameters, our unknown parameters, K, phi1, phi2, phi3, phi4, and so on. And also continue to next slide. And also we can guarantee an exponential rate for the consensus. So again, let's have a better look at the objective function. What does the objective function is really doing? The objective function, again, we use the observations we made before. We recall that we wanted K reduced, phi1 reduced, and some other parameters to be increased. So we use some other slack variables, theta1, theta2, theta3, and constrain the decision variables included in our unknown parameters to get some interesting upper bounds or lower bounds. So in this form, all upper bounds. But if we include 16 with 17, we get 18. And 18, if we look at 18, so K is upper bounded by some theta, phi1 is upper bounded by some theta, phi2 is lower bounded by a factor of theta, and phi3 again is lower bounded, so on. And if we minimize a weighted sum of theta1 to theta7, we reduce K, we reduce phi1, we try to increase phi2, and we get the MIT increased, as I just studied in the previous slide. So that was rocket in normal situation. And but we are interested to also see the impact of the DOS attacks. So how to deal with DOS, how to generalize our previous theorem in the presence of DOS. So DOS, in its presence, it blocks the communication channels between the agents. Also, when considering the local nodes, it blocks communication from sensors to other departments, to other blocks. So very, very simply, we can say it blocks all communication channels. D is the length of the attack in the given interval, N is the number of DOS in the given interval. So we should have some assumption on the duration of attack and on the frequency of attack. And also the closed loop multi-agent systems in the presence of healthy intervals, that is no attack, and attack intervals is going to be like this. This is the normal closed loop. However, this is due to attack, it becomes an open loop system. So we try to improve, generalize the previous problem to case of rocket, to case of DOS. Again, more or less the optimization is the same. So all of these constraints are the same as previous, but we include a new constraint. A new constraint with beta hopefully represent, gamma hopefully represent the DOS resilience level, and gamma with playing with zeta makes another parameter beta, and we include this new constraint. So this new constraint is kind of playing the role of the open loop behavior. And the theorem provides a DOS resilience to the given gamma. So gamma is given, and if we solve it, we are then guaranteed that a factor of duration of attack and a factor of the frequency of attack combined together should be less than gamma. And then consensus in the presence of DOS is guaranteed. And also we get, again, some kind of exponential guarantee. Okay, that was also the end of rocket. Let's briefly see some experimental results. We start first with Cs. We remember that Cs was for average consensus. We considered a network with 10 nodes, lambda 2 around 0.5, lambda 10, 8.5 again. We consider zeta 0.3 and H and phi2. Then if we solve that optimization parameter, we come up with K and phi1 as these numbers. So let's run consensus for a time horizon of 5 seconds with these given initial parameters 2i. This is the trajectory of the agents reaching average consensus. And this is the events, the pattern of the events. So we can see at the beginning, the events are intense. Then as we move on and the consensus is about to achieve, the number of events is reduced and the events are so sparse. So the number of transmissions are in the order of, 50, 60, 55. The average is 52. If it wasn't for the ATS scheme, we would transmit 500 packets. But thanks to the ATS scheme, only 52 of the packets are transmitted. So we can roughly say that 10% of the total packets are transmitted and 90% are saved. Okay. This is also another experiment for rocket. We consider a non-holonomic robot model, which is non-linear, but this is feedback linearizable. So if we do the feedback linearizable, we get a linearized model. The objective here is to get a regular pentagon. This is a kind of formation problem, a consensus-based formation problem to be more precise. So a change of coordinates are used to convert consensus to formation. Then we can solve our optimization. We can run our optimization with given parameters zeta 0.4 and DOS resilience level 0.3, and we get all these parameters simultaneously and at the same time. So we don't need to solve the optimization over and over. Just all of the parameters simultaneously came out from the optimization. And also an illustrative DOS attack is considered. So this is a kind of DOS pattern. Although our DOS can be unknown in nature, but just for illustration, let's see that DC is the start time of the DOS interval, and tau C is also the duration of the DOS interval. And these parameters, unknown parameters, are set in a way that the DOS attack is just about 0.3, just for sake of illustration. So this is the agents reaching the pentagon. I mean, we wanted to get the pentagon, and then the formation is reached on the pentagon. And also this is the transmissions. This is the events. The highlighted areas in pink are the DOS. So we know that there shouldn't be any transmission here because the transmission channels are blocked. As we can see, the dynamic event triggering results in a very sparse kind of transmission. The transmissions are very low, even after 20-25 seconds. This is also the trajectory of the dynamic threshold eta, which was included in the event triggering condition. So as we can see, eta starts from like 1, it rises a little bit, and after consensus or formation is about to achieve, it approaches 0. And again, the highlighted areas are the DOS intervals. This is also an interesting table in which we can show the trade-offs and how the optimization can really take care of the trade-offs between the consensus convergence rate and the amount of resilience that we want. So in the first section of the table, we fix gamma, which was the DOS resilience, the desired DOS resilience, and also we gradually increase the desired convergence rate. In the second part of the table, however, we fix zeta, and we gradually try to get more resilience with respect to DOS. IAE is the average number of transmissions here. T star is the consensus termination time, and AIET is the average inter-event time, AIET. So if we look at the results, increasing zeta, if we increase zeta as we expected, faster convergence rate is achieved, but at the expense of more frequent transmissions. I mean, a smaller AIET. So the events are closer together. I mean, the events are less sparse or more intense, we can say. On the other hand, if we increase gamma, we wanted to get more resilience. So of course, we should expect some performance drop in the consensus, and the performance drops are in the form of lower convergence rate and more frequent transmissions. This is also a brief, again, comparison for Rocket between one newly published transaction paper. It is a kind of paper which is similar to our work. It considers DOS attack, again, consensus event triggered, but it doesn't have, for example, dynamic event triggering. It doesn't have optimization. So I tried to make a good comparison in the sense of in the first part of the slide, in the number of transmissions, and in the second part, the guaranteed amount of DOS. In the first part, we can see that Rocket is roughly transmitting half of reference 1. So I tried to make everything like the network, the initial conditions, all of them the same to have a fair comparison. And also when considering the DOS attack, it turns out that Rocket can guarantee more realistic or higher upper bound for attack. And so we may wonder why is the reason? Because thanks to the optimization and thanks to the LMI that we use, the LMI takes care of the full information included in system matrix N and also decision matrix SP. But for example, in one, because they consider an explicit solution, they have to go with, I don't know, maximum eigenvalues or some kind of norms, and definitely it results in some sort of conservation. So yeah, that's it. Let's see some future direction, future work. So we talked a lot about dynamic event triggering. What if we include a sample data schema? I mean, we incorporate a sampler with dynamic event triggering. So I did this for average consensus, but not for more general agents. It is still an open problem. So SDET for more general agents, it can be a really good work. A distributed DOS attack also, in this work, I considered that some sort of centralized DOS attack. I mean, the DOS attack was either on or off. But if it is on, all communication channels are impacted. However, maybe in a smart kind of DOS attack, the adversary goes with a distributed situation in which that maybe one channel is blocked, the other channels are not blocked. So how to deal with this sort of problem is another future direction. Also, an observer-based resilient strategy can help in a more smooth and faster consensus as compared to the one that we considered in this paper. This is also a very interesting and new line of research. And also, if we consider multiple kinds of attack, multiple sort of attacks at the same time, it may be something very important and interesting. I mean, what if we consider DOS or false data injection at the same time? So two adversaries are there. And finally, just let me mention that in line with the future work and the line of research, a paper entitled "This Fault-Tolerant Periodic Event-Triggered Consensus Under Communication Delay and Multiple Attacks" is almost completed and on the verge of submission. So working over the years on consensus and ETC has resulted in a number of publications, in most of the time control venues and some other signal processing venues. And here I list the conference publications in ACC, American Control Conference, and some other ICAST. I think that's it. Thank you for your attention. And yeah, thank you.
Thank you.